Okay, so in this video, we will consider another application of the central limit theorem. So suppose we have the following situation. Suppose we have a regular four-sided die. So if you roll this die, if you imagine it, it would be a tetrahedron. There would be four faces and each one is a triangle. So if you roll this die, you will observe a figure, and you will observe either a 1, a 2, a 3, or 4. And suppose you roll this die, say, 50 consecutive times. So you roll the die once, then again 50 times. And every time you observe, let's say, since you have a tetrahedron, you would observe the figure on the bottom face. So you observe that figure, and every time you roll this die, you keep track of the figure on the bottom face. Then you would have 50 consecutive observations of numbers every time, either being 1, 2, 3, or 4. And what if you asked, what about the average of those numbers? So what if you roll the die 50 times? Every time you observe the figure at the bottom of the die, you add all 50 values. Each one is either 1, 2, 3, or 4, and then you find the average. So what if we looked at a probability regarding this average? So what if we wanted, so the probability that the average value, so we always use a bar for the average, so we'll use x bar. And again, we have here a random variable, because if you roll the die 50 times and you find the average of the faces, and I then myself roll the die another 50 times and find the average of what I have obtained, we most likely will not get the same average. So as you go through sets of 50 rolls and find the average of the figures observed, you will not get the same average every time. And that's why the average, that's why we use here in uppercase X, because it is a random variable. And what if we asked, well, what is the probability that the average will be, say, less than 2.6? So at most, 2.6. That is our question. Well, again, every time you have a probability involving a random variable, you have to figure out a distribution for it. Once you have a distribution, you find the probability with that given distribution. So here, well, how do we find the average? Well, if you think of it, we would have our first roll, and we would observe the figure from the first roll. But that number could be a 1, 2, 3, or 4. So every roll, every time we roll this die and we observe a figure, that is a random variable. So suppose that x1 is the result from the first roll. So x1 will be either 1, 2, 3, or 4. x2 is the result from the second roll up to, and here xn. And here we have 50 rolls. So n is equal to 50. So this is the result of the first roll, the result of the second up to the nth roll. And now, well, what distribution do the x's follow? x1, x2 up to xn, they are independent. Every roll is independent of the other rolls, and they follow a given distribution. Well, right now we don't really know what that distribution is, so we'll just say it follows some distribution. And suppose that the mean we call mu, and the deviation we call sigma. As we'll see very shortly, we'll have to find these. But for now, say that the average value of each roll is mu with a standard deviation of sigma. Now we can write the average as a sum of these 50 random variables over n. That's what the average is. So we take the figure from the first roll plus the figure that we have observed from the second roll up to the nth roll, keeping in mind here n is 50, and we divide by n. And now we ask, do we have a result that would allow us to obtain a distribution for this random variable? And the answer is yes. Firstly, because n is above 30, so we have 50 trials, so we're above 30 trials. So we can now use the central limit theorem. And also because we have an average of random variables. And remember, the central limit theorem is applicable if you have a sum of random variables, or if you have, as in this case, an average of random variables. So now we can quote the central limit theorem, which says the average will be approximately following a normal distribution with a mean. Well, if you remember, the mean of the average will be the same mean as the individual mean for each random variable. And the standard deviation of the average will be a little different though. It will be the deviation of the individual variables, the variables you're summing. But if you remember the statement of the central limit theorem for the average of random variables, it is the deviation of the individual random variables divided by the square root of the number of variables you're averaging over. And this is again coming from the central limit theorem. So now we can find the probability for this event that the average does not exceed 2.6, since we have a distribution for our average. It is a normal distribution, but now we need to find the mean and the deviation of the individual random variables. Well, we have to go back to square one. We have a discrete random variable in x1, x2 through xn. It is the same distribution, right? It is the result of rolling this four-sided die and observing the figure on the bottom. So we have to find the average and deviation of this random variable, which is again the result of the roll, of a single roll. So we have to construct our distribution table. I'll use here little x and big X. So I won't use x1 or x2 or xn because they all follow the same distribution. So suppose that x is the result of one roll. So we have the possible x values, and we have to find the corresponding probability. Well, every time you roll this four-sided die, the result will either be a 1, 2, 3, 4. And because the assumption was that the die was fair, that means that each figure has the same probability of occurring, therefore 1 out of 4. And of course, the total of these values is equal to 1, as it should be. Now that we have the probability distribution for a single roll, we can find the mean, mu, and the deviation, sigma. So let's find the average first. This is the quantity that we will need then to find the deviation. Well, the mean is very easy to find in this case. It will be, again, if you recall, summing over all x values, the value times the probability of the value occurring. Well, so 1 times a quarter is a quarter, plus 2 times a quarter, 2 quarters, plus 3 times 1 quarter, 3 quarters, plus 4 times a quarter, 4 quarters. If you add those up, you'll get 1 plus 2, 3, plus 3, 6, plus 4, 10. So 10 out of 4, which simplifies as simply 5 over 2. If you prefer in decimals, 2.5. So the mean is exactly 2.5. So now we have the mean. So we're halfway done. All we need now is the standard deviation for each roll. Well, let's first find the variance. If you remember, the variance will be the sum over all possible x values, and we sum the value minus the mean squared times the probability of observing this particular x value. So the first value is 1, so we have 1 minus 2.5. times the probability of observing 1, which is a quarter, so times a quarter means divide by 4, plus the next value of x is 2, so 2 minus the mean, which is 2.5, squared times a quarter, divide by 4, plus the third value 3 minus the mean 2.5, squared over 4, plus the fourth and final value 4 minus the mean, which is 3.5 squared, times a quarter, times its probability, divided by 4. And if we compute this, let's see what we get. So you can add those up, because it's all over 4, so you can add the numerators up, and then divide the whole result by 4. So we'll have 1 minus 2.5 squared, plus 2 minus 2.5 squared, plus 3 minus 2.5 squared, plus finally 4 minus 3.5 squared. This will give you 3. Oh, let me check again. I think I made a mistake. Let's start. Oops. Aha. My mistake here. Right, the mean was 2.5, not 3.5. So it's 4 minus 2.5. Let me compute this again. 1 minus 2.5 squared, plus 2 minus 2.5 squared, plus 3 minus 2.5 squared, plus 4 minus 2.5 squared. That is equal to 5 out of 4. So we have 5 out of 4. If you prefer, divide by 4, you get exactly 1.25. So the variance of the random variable that is the upper figure of a single roll is 1.25. Well, we wanted not the variance per se, but the standard deviation. So the deviation is the root of that. So deviation sigma is the square root of 1.25. Now again, you can evaluate this approximately, but keep the exact value and only evaluate after we will standardize. So now we can write our conclusion. So the distribution for the average of the 50 rolls, so x bar, our average, will follow, by the central limit theorem, approximately a normal random variable. The mean, if we just go up, was simply mu. We found that to be 2.5. So the average will have a mean of 2.5. And a deviation, and here was you have to be careful, it's not just sigma, but because we have an average, it is sigma divided by root of n. And here we were rolling the die 50 times, so there are 50 trials. So it's sigma over root of 50. So it's sigma root of 1.25 divided by the root of 50. And again, leave the exact answer and only round off when we get to standardizing the random variable. And now we're essentially almost done. We now have from the central limit theorem that our average random variable, so after we roll this die 50 times, we add the figures that we've observed for every roll and we divide by 50. We have asked what was the probability that our average does not exceed 2.6. Since we have now a distribution for the average, we can now find this probability. So recall what we have just derived. Our average random variable follows approximately a normal distribution by the central limit theorem. The mean is 2.5, and the deviation is the root of 1.25. Divided by the square root of 50. And we wanted the probability that the average obtained was at most 2.6. Well, since we want the probability involving a random variable that is normal, it is not standard. The mean, as you can see, is not 0. The deviation is not 1. We have to first standardize and then read out the probability from the table for the standard normal distribution. You can simplify this a little bit if you want, as an aside. If you write the root of 1.25 over the root of 50, that is the same as the square root of 1.25 over 50. And if you compute 1.25 divided by 50, you will get 0.025. So that's just the square root of 0.025. You don't have to do this, but here the number is nice enough, and now we have our standard deviation. So as always, to find the probability involving a random variable that is normal but not standard, we have to standardize. So for each side of the inequality, we have to subtract the mean. So minus 2.5, 2.6 minus 2.5. We subtract the mean and then divide by sigma, our standard deviation in this case, and that's the root of 0.025. And now, well, let's see what we have. We took a normal, or at least approximately normal random variable. If you subtract the mean, divide by its deviation, this becomes now the standard normal random variable. And recall that for this value, we will round up to the second decimal place. So 2.6 minus 2.5 is 0.1, divided by the square root of 0.025 will give you approximately 0.632. So we round up to 0.63. And now we're good to go. We are looking for the probability that the standard normal random variable is at most 0.63. And again, always visualize your normal distribution curve. So what are we looking for? The standard normal distribution is symmetric about 0, and it looks like a bell-shaped curve. And we want the probability of z being below 0.63. Recall it geometrically. That is the area to the left of the z-score that is 0.63, right? The probability of z being less than, therefore to the left of 0.63. So we want the area under the normal distribution curve below 0.63. And now this is exactly what we have from the table of the normal distribution. And since we have a positive z-score, we have to use the second side of our distribution table when the z-score is at non-negative. And our z-score was 0.63. So we look here, 0.6. And the second decimal place is red here, so that's 0.6. That's 0.61, 0.62, 0.63. So if we go down, 0.63, that's the z-score. And so the area to the left of 0.63 is 0.7357. And there you have it. The answer is 0.7357, which you can write in percentages as approximately 73.6%. And we're done. So what this says is, if you go back to the original problem, we had this regular 4-sided die. We rolled it 50 times. Every time we rolled a die, we observed the figure on the bottom face. Every time it was either 1, 2, 3, or 4. So we have in the end 50 values, where every single one is between 1 and 4. We found the average. So we've added all these values, divide by 50, and we ask, what are the odds? what is the probability that the average that we have obtained is at most 2.6? And the answer is, well, it's quite likely, 73.6% likely. And that is, again, a really nice application of the central limit theorem.